Yes, it is all right, right? So I will be presenting the screen, sir. Uh, so from here, so like we tried earlier. Am I audible?
Yeah, I can hear you.
Okay, so what I said, I will be presenting the pages actually from here,
Oh,
right? So you can speak accordingly. That we tried already. It will be okay.
I don't think I saw the pages the last time at all.
Okay. So would you like to? You can also switch on your video. You can read. So you
Very
can.
good evening, sir.
Yes.
Morning, sir.
Hello. Very good evening, sir.
All three organizers.
Uh, Hello. Can you hear me? Dear
Of
sir.
course.
Okay.
Yes.
Actually, at your place it's night, and in our place it's early morning. Actually, morning.
Well, it's not quite 9 o'clock here yet.
Yeah, it's
It's
morning.
nighttime.
Yes,
know.
yes, sir. At your place it's 9 p.m. actually.
That's right.
Yes.
Can verify that.
So we are just going to start in 1 or 2 minutes.
Yeah.
So sir, he's Dr. Pal Pandey. He's also one of the coordinator. So he shared that emails.
Hello, sir. Good evening, sir.
Yes.
Can you hear me, sir?
Yes.
Good evening.
Shall I put on a more formal shirt?
Sorry,
Yeah.
sir?
Shall I put on a more formal shirt? I can do that.
Yes, sir. Yeah.
Okay, I'll do that.
No. He is asking forward, sir.
Sorry.
Whether he wants to be the forward or
No, if he wants, you let him.
okay.
There. How can I?
Okay, so Professor Veer, can we start the session now?
No, he's not. Okay, he's here.
I'm here.
Okay, so a very good morning to all of you. I welcome you on day 3 first session. Our distinguished speaker, Professor Beer, for this session is already with us. He is a very well-known mathematician. It is our honor to have Professor Beer as one of the guest speakers of this workshop. I request Dr. Varun Jindal to please formally introduce Professor Beer to our participants.
Yeah, thank you, ma'am. So a very good morning to one and all present here. It is my honor to introduce Professor Beer to the participants. So Professor Beer did his PhD from University of California, Los Angeles. He retired as a full professor at the California State University, Los Angeles, where he won the President's Distinguished Professor Award. He has around 140 research papers in various international journals, and he is the author of two very popular books. One is on applied calculus for business and economics, and second is on topologies on closed and convex sets, which is also one of the basically the talk will be based on probably the content given in this book. He's on the editorial board of two prestigious journals, Journal of Convex Analysis and Set Valued and Variation Analysis. He had visiting positions at various universities in America and Europe. To name few, he had a visiting position at University of California, University of Minnesota, and also the Auckland Institute of Technology in New Zealand. A conference honoring Professor Beer was held in Verona Lake Como, Italy on his 65th birthday. So it is our pleasure to have Professor Beer here. So today he will be talking about hyperspace topologies, broadly speaking. So in more precisely, he will be dealing with the topologies on closed subsets on a metric space X, D, and using the topologies will be defined using distance functionals with various Born logies. So I formally invite Professor Beer to please start the talk. So I will be sharing the pages from here. Thank you.
Thank you, Varun. It's a pleasure to come back to Jaipur, but the only time I was there was as a tourist. And I know how beautiful of a city it is, and it's a pleasure to come as a mathematician. And I am grateful to the organizers to invite me to participate. I'm going to be talking about topologies on non-empty closed subsets of a metric space. I won't talk about all topologies, but this talk will serve as an introduction to the topic for those of you who don't know much about it. And this was my major area of interest up through, let's say, 1995. My interests have changed somewhat. I'm now interested more in Bornologies and Lipschitz analysis, and I'll have a book coming out shortly on that. So we'll start with the metric space, and it'll be denoted by XD, and all metric spaces will have at least 2 points. I may forget to say that, but that's to be understood. So the non-empty closed subsets of X will be denoted by C0 of X. If the 0 weren't there, it would be all closed subsets. And so we're going to look at functions, distance functions that we're going to associate with our closed subsets. And when I write D dot A, it's the usual distance function for the set A. And I can think of these distance functions as sitting in the continuous functions from R. Or if you want just the real valued functions, on X. And I'll be looking at three basic topologies of uniform convergence on the function space that the closed sets will inherit out of this identification. First is the topology of pointwise convergence. If you have pointwise convergence, then you have uniform convergence on finite subsets. So you might as well be thinking of it that way, because the finite subsets form a Bornology. And the second topology we'll look at is the topology of uniform convergence. And this is uniform convergence on the Bornology of all subsets of X, in other words, the power set of X. And then finally, we'll be looking at the topology of uniform convergence on the Bornology of bounded subsets of X. By bounded, I mean metrically bounded in the usual sense. And maybe I should say what a Bornology is for those of you who don't know what that word means. A Bornology is a family of subsets of X, which has three properties. First, it contains the singletons. Second, it's hereditary. And third, it's stable under finite unions. Now, these three topologies are called in the order that I gave them: the Weismann topology, the Hausdorff metric topology, although some people would prefer other terminology, and the last one, topology of uniform convergence on bounded sets for these distance functions, is called the Yatoush-Wetz topology, but it's also called the bounded Hausdorff topology by some. Yatoush and Wetz are both still alive. Weismann is not, and of course Hausdorff is not. So again, D dot A is the usual distance function for a set A, and it's defined as follows. If little x is in capital X, dxa is the inf of the distance from little x to little a, where little a runs with capital. And when I use the word hyperspace topology, I'll mean a topology on the closed subsets, such that the map which sends little x to singleton x, thought of as a closed subset, is an embedding. And often we say that that the fact that x to singleton x is embedding, we say that the topology is admissible. You'll hear that language used. And each of our three topologies that we'll talk about meet this requirement, also some auxiliary topologies. Almost all the material that I'm going to talk about is in my 1993 monograph, Topologies on Closed and Closed Convex Sets. 1993 is a while ago. But this is not an area where a lot of work has been done in the following years. So let's start with some preliminaries. Again, all our metric spaces will have at least 2 points. By R to the X, we mean the set of all functions from X to R. And C of XR will be the continuous functions from X to R. And of course, R is understood to have the usual topology. If A is a non-empty subset of X, then the distance function for A is continuous because of the inequality that you see right there. The distance between the function values is less than or equal to the distance between the inputs. So this means that the distance function for set A is a 1 Lipschitz function. It's Lipschitz with constant 1. You can also say that the function, the distance function, is non-expansive. So let's start with a point in X, P, and let alpha be a positive scalar. We'll denote the open and closed balls with center P and radius alpha by SD round bracket P alpha for the open ball and SD square bracket P alpha for the closed ball. By the open alpha enlargement of A, we mean the union of all the open alpha balls whose centers run over A. So this will be an open set. Sometimes it's called a ball about A, but I like the word enlargement. I think most people use that. We call a subset A of X bounded if it's contained in a ball. And if A is non-empty, then A is bounded if and only if its diameter with respect to the metric D, defined in the usual way, is a finite number. You can also say that the empty set has diameter 0 if you want, but I don't think that'll come into play here. So we'll now go to the next page. A subset A is called totally bounded if for every epsilon greater than 0, A is contained in a finite union of epsilon balls whose center runs over X. Excuse me, I didn't say that correctly. A is contained in the enlargement, epsilon enlargement of the finite set, where the finite set is called F epsilon. Epsilon is allowed to be anywhere in X. And but if that is true for every epsilon, then actually the set to F epsilon can be chosen to be in A. So the totally bounded sets form a Bernoulli. That's easy to verify. If A and B are non-empty subsets of X, by the excess of B over A, we mean, well, there's two ways of thinking about it. It's the soup of the distances from B to A as B runs over A, or it's the inf of the radii of the enlargements of A such that B is contained in them. And I should note that the excess of B over A doesn't have to equal the excess of A over B. It's not a symmetric function. And another functional in the same vein. Oh, I should say also this excess functional can have infinite values. So for example, if I take two lines in the plane with the Euclidean metric and they intersect in one point, then the excess of one over the other will be infinity. By the gap between two sets A and B, again, they're thought of as non-empty, I mean the inf of the distance of points of B to the set A, which is the same thing as the inf of D of AB, where A runs over A and little b runs over B. And dxa, as we defined it initially, that is the distance from X to A in the usual sense, is the same as the excess of singleton X over A, and it's the same as the gap between singleton X and A. So there are two important formulas that describe excess and gap. The first one's much better known than the second. The excess of B over A is the soup, as X runs over X, of D of XA minus D of XB. So the excess of A over B would have those two terms, dxa and dxb, reversed. And if I take the maximum of those, notice that's just the uniform distance between the distance functions. I'll come back to that, but I just wanted to point that out at this time. The second formula is a formula for gap between B and A. And this is not so well known. A lot of people know one, but two, not so many, even though it's in my book. We won't use that for anything, but I thought it'd be worth mentioning. By an extended metric D on a set X, again, X has at least 2 points, we mean a function on X cross X into the extended non-negative reals that satisfies the usual axioms for a metric. But of course, you can have values of infinity. And we can, as an example, look at the metric or the extended metric of uniform convergence on R to the X. So if I have two elements of R to the X, these are functions from X to R. That's given as the sup X and F, absolute F of X minus G of X. And that, of course, can be infinity. I'm not assuming the functions are bounded. I'm not assuming they're continuous. But as you would with bounded functions, next slide, we'll call this extended distance the uniform distance between F and G. So for example, if X is R, and if I talk about the real line, again, I'm always assuming the usual Euclidean metric. If F of X equals X and G of X equals 2X, then the uniform distance between the two functions is equal to infinity. You can get arbitrarily large vertical gaps between the two graphs. If, on the other hand, H of X is X plus sine X, then the uniform distance between F and H is 1 because sine X varies between -1 and 1. So retaining our notion of balls of finite radius introduced before, a subset of X, X is an extended metric space, is declared open if it contains a ball of finite radius about each of its points. And you can then talk about the topology determined by an extended metric. And this topology is metrizable in the usual sense because I can replace this extended metric by the minimum of D in 1. That'll be a bona fide metric and it'll give you the same open sets. So in an extended metric space, we can talk about boundedness, total boundedness, completeness, things like this. You might wonder, why not just replace this D by a finite metric and just be done with it? I mean, what's the advantage of keeping D? Well, you might be interested in the large structure of the extended metric space, and that is obliterated when you make this replacement. So I really don't like to do that. So now we'll talk about the Wiseman topology. Again, we're going to focus on 3 topologies. There are other topologies I won't even talk about. But there will be some auxiliary topologies that I will talk about. So R to the X, again, is the set of all functions from X to R. And we can think of that as a product. It's X copies of the real line. And we can equip it with the usual product topology. And the product topology is the weakest topology, such that all of the projection maps, and there's a projection for each X and X, are continuous. So a net in R to the X is we'll call it F lambda. So lambda runs over some directed set, is convergent to a function X, provided for each X and X, the projections pi X of X lambda converge to pi X of F, which means that F lambda of X converges to F of X. And so for that reason, the product topology is often called the topology of pointwise convergence on R to the X. That's That's what we mean by the topology of pointwise convergence. And then, you know, as with usual product topology, we can describe a base for the open sets. And I've given an example of a typical basic open set. So V1, V2 up through Vn are open sets in the line. And then I have the following intersection from those using points x1 through xn and x. So what does it mean to be in there? That means that f of x1 is in V1, f of x2 is in V2, all the way down to f of xn is in Vn. So that's what a typical open set looks like in the topology of pointwise convergence. So the Wiseman topology, tau WD, on the non-empty closed sets is a topology inherited from this product equipped with the topology of pointwise convergence under the identification we talked about. And this was considered in a paper by Robert Wiseman in Finite Dimensions, a famous paper in convex analysis that I don't want to talk about. By definition, a net of non-empty closed sets is Wiseman convergent to a non-empty closed set if and only if we have pointwise convergence of the distance functions, a lambda to the distance function for a. And it's a routine exercise to show that x lambda converges to x in the metric space xd if and only if singleton x is the Wiseman limit of singleton x lambda. So the topology is what we call a hyperspace topology. You have this admissibility property. It's really important to note that the pointwise convergence of a net of distance functions doesn't ensure in general that the limit function is a distance function, even if it's continuous. And this can even happen for sequences of closed sets in a complete metric space. So I want to give you an example of that. So again, what I'm saying is the pointwise limit of distance functions, even for sequences, need not be a distance function in general. So let's let our metric space be the set of whole numbers, 0, 1, 2, 3, and so forth. So it's 0 union the natural numbers. And I'll define my distance between distinct points as follows. The distance from 0 to any n bigger than or equal to 1 is 2, whereas the distance between distinct positive integers will be 1. So this gives a discrete topology on my underlying set X. And there aren't any Cauchy sequences, so I have a complete metric. So for each positive integer n, let an be the set 0, n, n plus 1, n plus 2, and so forth. So the ans are getting smaller and smaller as I increase n. So the sequence d dot an is, there's a t missing in pointwise convergent to the characteristic function of the natural numbers. If I look at 0, d0 an is 0. And if I look at any other number like 17, d17 an is eventually 1. So that's why you get the characteristic function of the natural numbers. But that's not a distance function for any set. Now, if you have A lambda converging to A in this sense, there's a way to describe the limit set without reference to the distance functionals at all. So given a net of non-empty closed sets, A lambda, we'll define the closed set subsets. Some people would say lim inf A lambda and lim sup A lambda. Others would call these things, the lower closed limit of A lambda and the upper closed limit of A lambda. Depends what books you're looking at. I'll shade the shorter things though. So lim inf A lambda will be the points in X such that each neighborhood of X hits A lambda eventually. Whereas lim sup A lambda will be the points of X, each neighborhood of X hits A lambda frequently. So it's easier to be in lim sup A lambda than it is to be in lim inf A lambda. And so therefore lim inf A lambda is contained in lim sup A lambda. Elements of lim inf A lambda are called limit points in the net of sets, whereas elements of lim sup A lambda are called cluster points in the net of sets. And it's really quite easy to show that if A lambda converges to A in the sense of Weismann, then you have A being at once lim inf A lambda and lim sup A lambda. And that equality string is called Kuratowski-Panlevé convergence in the literature. Some people just call it Kuratowski convergence. Example 3.2 shows that the converse can fail. So these sets that we had, AN, do converge in the Kuratowski-Panlevé sense to just singleton zero, which is A. So a question to ask is, when is it the case that if you have Kuratowski-Panlevé convergence of a net of closed sets, you can be sure that you also get Weismann convergence? And this question was answered a long time ago. It's pretty simple. Let's call a ball in a metric space proper, if it's a proper subset of the metric space. And we say XD has nice closed balls if each proper closed ball in X is compact. It doesn't say that if X happens to be a ball itself, it may not be compact for this to be satisfied. So the necessary and sufficient conditions are given by theorem 3.3 at the top of the next page. Let XD be a metric space, then Kuratowski-Panlevé convergence ensures D Weismann convergence if and only if XD has nice closed balls. Now it turns out I can't. I've got a lot of things to cover. Another question you might ask is, well, what metrizable spaces have compatible metrics that have nice closed balls? Well, you can see that if a space has nice closed balls, then it's locally compact. And it turns out that the converse is also true. In other words, if you have a locally compact metrizable space, then there'll be a metric which has nice closed poles, which is compatible with the topology. So the first people to seriously work on the Wiseman topology were Alec Lahiski and Sandro Levy. And these are both my friends. Lahiski is originally from Poland, but lives in Germany. And Sandro Levy is Italian. They realized in their first paper that the Wiseman topology is metrizable if and only if the underlying metric space is separable. That means that there's a countable dense subset. Let's suppose that's xn, where n runs over the positive integers. So a compatible metric is given by the displayed formula. The 1 is put in there so that the series converges. And it turns out in this case that the non-empty closed sets equipped with this metric is also separable metric space. And one of the things that I did that is one of my more popular results in topology is that I proved that if this underlying metric is in addition complete, along with being separable, then the Wiseman topology is completely metrizable. I'm not saying that the metric displayed there is a complete metric, but there'll be another one. And subsequently, Camillo Costantini, who is a student of Sandro Levy, showed that if XD is separable and there is an equivalent complete metric, in other words, X is a so-called Polish space, then the initial Wiseman hyperspace is still completely metrizable. In other words, the 1 associated with the metric D. Equivalent metrics on a set, metrics that give rise to the same topology, or if you want the same convergence sequences, can determine different Wiseman topologies. So if I look at the standard 0, 1 metric on the set of whole numbers, this is equivalent to the metric that I displayed for you. But you do have Wiseman convergence with respect to rho, where you didn't with respect to D for that sequence A and in fact, D and rho are uniformly equivalent. So this is kind of disturbing. But for a long time now, maybe since, I don't know, 1988 or something, necessary and sufficient conditions for equivalent metrics on a set to determine the same Wiseman topology were identified. And the authors here are Costantini, Levy, and Ziaminska. I've never met Ziaminska. This is something I thought was sort of an unexpected condition that they found. I think there are other ways of describing when metrics have the same Wiseman topologies, but they remain to be discovered. I don't think these are the best conditions. I've been saying this for 25 years and no progress has been made. So let's let XD be a metric space and suppose, this is a definition, suppose A and B are non-empty subsets with A contained in B. We say that A is strictly D included in D, provided there exists a finite subset of B and positive numbers, suppose there are n elements in the subset. So we have positive numbers epsilon I and alpha I. Epsilon I is less than alpha I. I goes from 1 to n. Such that A is contained in the union of the balls of radius epsilon I, which is contained, of course, in the balls of radius alpha I with the same centers, and in turn they're contained in B. So now here's the characterization of Levy, Costantini, and Ziaminska. Let D and rho be equivalent metrics on a non-empty set, then they give the same Wiseman topologies if and only if each proper open D ball, strictly rho includes each open D ball of smaller radius, and then the other way around. Of course, if I just had one of those conditions, then I'd have inclusion, but I thought I would state it in terms of equality of those topologies. So we've seen with our simple space consisting of the whole numbers that equivalent metrics, in fact, uniform equivalent metrics, can determine different Wiseman topologies. So let's let now delta of x denote the family of metrics that are compatible with the metrizable topology tau on a set X. So these elements of delta of x are all equivalent metrics. So the question to be asked is, what is the smallest topology containing all of the induced Wiseman topologies on C0 of x, determined by members of delta of x, look like? So again, different members of delta of x can give rise to different Wiseman topologies. And if I take the supremum of them, in other words, the topology generated by all of the Wiseman topologies, what does it look like? And this question was answered by these four authors. So you got a new name there. It's an Indian name, Sam Nepali, who grew up in Mumbai. Wasn't called Mumbai then. He's passed away. And it was a pleasure for me to give a memorial address at IIT Bombay upon his passing. So let's let x tau be a metrizable space. Again, delta of x is going to be all of the compatible metrics. The smallest topology on the non-empty closed sets containing all of the Wiseman topologies can be described as a so-called hit and miss topology. It has a subbase consisting of all sets of the form A and C0 of x, such that A hits V, where V runs over the open sets, and plus all sets of the form A and C0 of x at A is contained in V, where V runs over the open subsets. So these aren't the open subsets. You have to take unions of finite intersections of these. And this topology was first studied in depth by the American topologist Ernest Michael. He called it the finite topology, but it's usually called the Vietoris topology. One of my prized possessions was a letter that I received maybe around 1980 by the German mathematician Vietoris, written to me in German. Somebody translated it for me once because I don't read German, but still I was very happy to have this. So this finite topology is one of the two most best known topologies on closed subsets. So now we'll talk about the Hausdorff metric topology on C0 of x. That's the other one, which is particularly well known. There's a third one I won't talk about today, the so-called Bell topology. So what about Hausdorff distance? So the Hausdorff distance between non-empty closed subsets A and B. I think I've already said this at the beginning. It's a uniform distance between the distance functions. So Hausdorff distance is compatible with an extended metric on R to the X. And convergence means uniform convergence of distance functions. And we denote the associated topology by tau HD. So this is finer than Weismann topology because uniform convergence is a stronger requirement than pointwise convergence. So given our formula for the excess of one set over another in a metric space, which we spent some time talking about, Hausdorff distance is the maximum of the excess of B over A and the excess of A over B. So this can be infinite. So like, for example, if A is bounded and B is unbounded, then you're going to get an infinite Hausdorff distance. Next slide. And you can express Hausdorff metric convergence. Again, it's an extended metric, but it's still called Hausdorff metric convergence. We can express it in terms of enlargements. For every epsilon greater than 0, the epsilon enlargement of A lambda contains A, and the epsilon enlargement of A contains A lambda eventually. Both of those things have to happen. And this is the way people usually think about Hausdorff metric convergence. So when restricted to the non-empty closed and bounded subsets, Hausdorff distance becomes a finite valued metric. And some people call this the Hausdorff-Pompeiu metric. Pompeiu is a Romanian. And he formulated distance in an equivalent way. Instead of taking the maxes of the excess, he took the sum of the excesses. And I don't want to do that, even though I'm continually urged by Romanians to do that, because the Hausdorff metric convergence has better properties. The Pompeiu metric doesn't give the uniform distance between the distance functions. And also, the map which sends X to singleton X is not an isometry with respect to the Pompeiu distance, where it is with respect to the Hausdorff metric distance. I'm not asking you to agree with me, but that's a choice that I've made, and I've paid a price for that. The space of non-empty closed subsets equipped with Hausdorff distance reflects many of the properties of the underlying space. So if the non-empty closed sets are complete or totally bounded, then the same is true for the hyperspace. And therefore the hyperspace will be compact if and only if the base space is compact, because compactness is characterized by completeness and total boundedness. So I want to describe the Hausdorff metric topology as a weak topology in two different ways. These are expressed in theorem 4.1 and 4.2. The Hausdorff metric topology is the weakest topology on the non-empty closed subsets, such that for each non-empty closed subset B, the excess maps, where B is the fixed left argument and B is the fixed right argument, are both continuous. And as a companion theorem, the Hausdorff metric topology is also the weakest topology on the non-empty closed subset, such that for each B in C0 of X, the maps, these two maps here, the excess map where B is the fixed left argument, and the gap map, where B is the fixed left argument, are both continuous. I can't replace in this formula the assignment A to E, D, B, A by A to E, D, A, B. They both have to be, well, the first one has to be, the fixed argument has to be on the left. Equivalent metrics for metrizable space need not determine the same Hausdorff metric topologies. As for the Wiseman topology, oh, maybe I'll say one more thing about the Wiseman topology. The Wiseman topology can also be thought of as a weak topology. The generating functions are the functions dx dot, where x runs over x. And the dot is filled by a non-empty closed set argument. And some people like to think of the Wiseman topology in that as a weak topology. So as I said, equivalent metrics for a metrizable space need not determine the same Hausdorff metric topologies. So let's look at R with the usual metric D, and then R with another metric rho. Rho of XW is defined by that formula. So here's what I'm doing for my rho distance. There's a natural one-to-one onto map of R from R to -1, 1, sending x to x over 1 plus absolute x. And so what I'm doing is I'm applying that map. That's a homomorphism. And then I'm using the usual Euclidean metric in -1, 1. So I'm getting a metric which is equivalent to the usual metric on R. So let's put A as a set 2n, n, and n. And as a sequence of closed sets, which may or may not converge to A, I'll let AN be A union the integers which are at least n. Now this fails to converge in Hausdorff distance with respect to the usual metric to A. But it does converge in the in this auxiliary metric rho in the Hausdorff distance. So this brings up the question again, as we had for the Wiseman topology. What are necessary and sufficient conditions on metrics so that we get agreement of the induced Hausdorff metric topologies? And this result is most easily proved by the Ufremovich lemma. This is in my book, and the whole thing is proved out. But I don't know who did this first. So when I put this in my book, I just wrote it out myself. Maybe John Isbell knew this, but I don't know. If someone knows, let me know. I'd like to know who's responsible for this theorem. So let X tau be metrizable and let D and rho be compatible metrics. The following conditions are equivalent. The metrics D and rho are uniformly equivalent. This means the identity map is uniformly continuous in both directions. 2, the Hausdorff metrics on C0 of X are equivalent. 3, the Hausdorff metrics on C0 of X are uniformly equivalent. So it's a much more obvious condition to look at than in the case of the Wiseman topology. So our next two results concern the comparability of the Hausdorff metric topology with this hit and miss Viator's topology that we talked And both of these conditions can be found in this paper of Ernest Michael. Well, I guess in theorem 4.5, I include condition 2, which relates the Hausdorff metric convergence, Hausdorff metric topology, and the Weismann dimension. So the following are equivalent. The Viator's topology is finer than the Hausdorff metric topology. The Hausdorff metric topology coincides with the Weismann topology. And 3, the metric space XD is totally bounded. Okay, that's fairly transparent. In terms of the other inclusion, it's not so transparent, but for people who've been doing metric space topology for the last 20 years, it's not something that's unexpected, but the time that Michael came up with it, it sure was. Let XD be a metric space, then the Hausdorff metric topology contains the Viator topology if and only if X has a particular structure. And there are other ways of describing X, which I'll get to, but this is the most visual. 2 properties have to hold for X. The set of limit points of X is compact. Maybe empty, but it's compact. And for every epsilon greater than 0, there exists delta greater than 0, such that if I take a point outside the epsilon enlargement of the set of limit points, then the delta ball about X will contain only X. In other words, the set of points outside of the epsilon enlargement of the set of limit points is uniformly isolated. And spaces that satisfy this visual condition are usually called UC spaces, or sometimes Atsuji spaces, or sometimes Lebesgue spaces. And there's so many characterizations of these spaces. I'm just going to give you a few that you'll recognize are properties of compact metric spaces. They're not characteristic. For the most complete and up-to-date set of characterizations, I would consult Subhaman Kundu and his students, prior students. All right, so these are some other ways of describing the metric spaces, which I've called UC spaces. Now I'm giving you properties that compact spaces all have to have, but it's not characteristic. First one, each open cover X has a Lebesgue number. That means there's a number lambda such that if I have a subset of X of diameter less than lambda, it lies totally within one member of the cover. Second property, whenever Y rho is a metric space and F is a continuous function from X to 1, then F is uniformly continuous. In a standard analysis course, you prove if X is a compact metric space, and you have a continuous function from X to another metric space, it's uniformly continuous. But that's not characteristic of compactness, obviously. I mean, take a look at any continuous function, actually any function's continuous, on the integers as a metric subspace of the real one. That'll be uniformly continuous. And that's a UC space. Third property. It's true for real valued functions. If it's true for real valued functions, then it'll be true for functions into any second metric space. Fourth, whenever f is a non-vanishing real valued uniformly continuous function on x, its reciprocal is uniformly continuous. Now this is fairly recent. This was discovered in 2018 or published in 2018. All the other things that I've written down there were published before 1960. Fifth property. If I have a pair of disjoint non-empty closed subsets of this, then there's a positive gap between them. That's something you prove for compact metric spaces. But again, it's not characteristic. Each UC space, we've said each compact space is UC, but also each UC space is complete. That's easy enough to prove by condition 5. If you have a Cauchy sequence, you want to show it converges, you can assume that the terms are distinct. Well, all you have to do is show it as a cluster point. If it doesn't have a cluster point, then the set of terms is going to be a closed set. And you can look at the even set of even terms with even indices and the set of terms with even odd indices. There'll be two disjoint closed sets for which there's not a positive gap between them. Well, that's why I use C space is complete using property 5. And it turns out that a metrizable space has a compatible UC metric if and only if the set of limit points is compatible. I proved this in a paper. I gave a very simple construction of sets of metric in a paper I published more than 30 years ago in the American Mathematics. But the construction of the metrics also mentioned in my book. Okay, so what about Hausdorff metric topology as a useful tool? Well, most researchers realize that the Hausdorff metric and the associated Hausdorff metric topologies are too strong when working with it unbounded sets. In other words, unnatural things happen. It's too hard for things that ought to converge to not converge. So for example, in the Euclidean plane, if L is the line with equation y equals 0, in other words, a horizontal axis, and Ln is a line that goes to the origin and slope 1 over n, you'd want Ln to converge to L, but it doesn't in Hausdorff distance. And the Vietoris topology is even worse behaved. There's nothing I like about the Vietoris topology. So for example, you should verify that if you look at the sequence of lines, Ln has equation y equals 1 over n. That ought to converge to the horizontal axis in the Vietoris topology. It does in the Hausdorff metric topology, but it doesn't converge in the Vietoris topology. In my opinion, topologists too often study things simply because they're there, not because they're natural or useful. And that's why I don't consider myself a topologist, because I won't do that. Given my metrizable space, x tau, what does the smallest topology containing each of the Hausdorff metric topologies look like, where D runs over the compatible metrics? Again, if you don't have uniformly equivalent metrics will get different Hausdorff metric topologies. And a description of this topology as a hit and miss topology was discovered by the 4 authors listed. So Charlie Himmelberg and Fred Van Vleck were at the University of Kansas, and Carol Prickery was at the University of Minnesota. Let X tau be a metrizable space, and the smallest topology on the non-NP closed subsets, containing all of the Hausdorff metric topologies, has as subbase all the sets of the form A in C0 of X, such that A is contained in V, where V runs over the open subsets of X. Well, that's a part of the generators for the Viator's topology, but it's the other part that's different. You attach to that all sets of the form A and C0 of X, such that A hits V, where V runs over a family of open sets V, which are locally finite. A locally finite family of open sets means that at each point of X, you can find a neighborhood which only hits finitely many of those. And this topology is called the locally finite topology. So I want to do some applications because I'm really interested in applications. So I'm going to talk about a little convex analysis here. This won't hurt. Consider a real norm linear space. Let A be a non-empty subset of the norm linear space. Then the smallest convex set containing it is called its convex hull. And it's denoted by CONV parentheses A. And it consists of all convex combinations of elements of A. So a convex combination is a linear combination using non-negative scalars that sum to 1. So that's the smallest convex hull of us, the smallest convex set containing A. And X star will be the continuous dual of X, and U will be the closed unit ball in X star as determined by the usual operator. The support functional for a non-empty set A doesn't have to be convex, is defined on X star. It's a function on the dual space. And I'll call it, different people use different notations for this. I'll call it S dot A. And the dot is filled by elements of the dual space. So S of X star of A is the soup of X star little a as A runs over capital A. And, you know, depending on what A looks like, that can be infinite. So let's take a look at a simple example. So let our norm linear space be R2 equipped with the usual norm. It's self-dual. It's a Hilbert space. Each continuous linear functional is given by a dot product with a fixed member of R2. So let's let A be the integer points on the horizontal axis. Then if I take an element of the dual space of the form 0y, then the support function will be 0, because if I take its dot product with any element of A, I'll get 0. On the other hand, if y is non-zero, then the support functional will take on value infinity. Each support functional is a positively homogeneous, subadditive, lower semi-continuous convex function. Actually, convex function is redundant. If it's positively homogeneous and subadditive, it'll already be convex. And it'll have values in the extended real line. It won't have value minus infinity, but it could have value infinity. And I don't get anything different if I replace A by its convex hull. So in that above example, I could replace the A that I have by the horizontal axis. Get the same thing. And if A is bounded, then its support function is finite valued and continuous on X star with respect to the operator. So the following result is due to Lars Hormunder. It's a very old resort and uses a separation. I think this is really attractive. It looks like I have another notational problem. I'm missing double bars on my norm linear space here. So let's let X double bar dot double bar be a real norm linear space. And the map that sends A to its support function, restricted to the closed and bounded convex sets in X, is an isometry from these sets equipped with Hausdorff distance to the continuous functions on the dual space restricted to the unit ball equipped with uniform distance. So the distance between two support functionals, I restrict them to the unit ball, and I take the uniform distance between them. So I found this result attractive. I guess I learned it when I was 20, maybe 23, and chose to study convexity. And now we'll move to the Atouche-Wetz topology on C0F. This is intermediate in strength between the Wiseman topology and the Hausdorff metric topology. Again, we identify a closed subset A with its distant function. But now we're going to use the topology of uniform convergence on bounded sets. So if I fix P and X, a natural metric compatible with the Atouche-Wetz topology is given by this formula. I'll get one in there to make sure that the series converges. Now, unlike Wiseman topology, if I have a uniform convergence of distance functions on bounded sets to a function, the function will be a distance function. That's critical. That's a strong argument for using the Atouche-Wetz topology against the Wiseman topology. That'll occur in a complete metric space. And that will force this metric actually to be a complete metric. But that's not how Atouche and Wetz thought about convergence in this topology. Not at all. These kinds of metrics and this association with distance functionals came about after a year or so. Here's how they thought about Atouche-Wetz convergence. So suppose I have a net A lambda of non-empty closed sets and a potential limits set A, non-empty closed. What does it mean for A lambda to converge to A in the Atouche-Wetz sense? Whenever B is bounded, then B intersect A is eventually contained in the epsilon enlargement of A lambda, and symmetrically B intersect A lambda is contained in the epsilon enlargement of A eventually. And this is an admissible topology, just like the others are. So again, this is how Tooth and Wetz initially conceived of it. But they were particularly interested in nets of extended real-valued lower semi-continuous functions on a space. And they associated each function with its epigraph. The epigraph consists of those points in X cross R, X alpha, where alpha is greater than or equal to f of X. And lower semi-continuity corresponds to having a closed epigraph. And for this reason, they call it the epidistance topology. But I'll come back to this in more detail. But I guess I should say that applied mathematicians don't think of lower semi-continuous functions as their graphs. They think of them as their epigraphs. Well, actually, I think of it that way. So what about agreement of the Atouche-Wetz topology with the others? Let XT be a metric space, the following are equivalent. Each bounded subset is totally bounded. 2, the Atouche-Wetz topology agrees with the Wiseman topology, the weaker Wiseman topology. 3, the Atouche-Wetz topology is separate. So in particular, this is true in Rn, because in Rn, each bounded set is totally bounded. Now, in terms of agreement with the Hausdorff metric topology, this won't be a surprise. The Hausdorff metric topology agrees with the Atouche-Wetz topology if and only if D is a bounded metric on X. Now, what about agreement of two Atouche-Wetz topology as determined by equivalent metrics on X? When does that happen? Well, 2 conditions have to happen. So D and rho are equivalent metrics. For the Atouche-Wetz topologies to agree, 2 things have to happen. First, you got the same metrically bounded sets. And second, the identity mapping between the metric spaces, of course, the set in which the metric defines is the same, is bi-uniformly continuous when restricted to bounded subsets of X. And the idea of bounded subsets of X is well defined by 1. And one of the interesting things that I didn't think it was so important at the time, but I had fun doing it. If X tau is a non-compact metrizable space, then if you look at the set of compatible metrics, it will have an uncountable subfamily, call that delta 1 of X, such that if you take any 2 members of this uncountable subfamily, you get different metric chronologies. So that means there's uncountably many distinct Atouche-Wetz topologies as determined by compatible metrics when the space is not, metrizable space is non-compact. On the other hand, if you have a compact metrizable space, Well, you know, in a compact metrizable space, any two compatible metrics will be uniformly equivalent. And each member of delta X, of course, is a bounded metric. If a compact metric space, the diameter of the space under that metric will be finite. So any two Atouche-Wetz topologies agree, and they agree with the Hausdorff metric topology. The unique Hausdorff metric topology is determined by delta X. Because if you take two elements of delta X, two different elements, they'll be uniformly equivalent, so you'll get the same Hausdorff metric topology. So really different things happen depending on whether the space is compact or non-compact. So I want to talk about some applications of Atouche-Wetz topology, again, to geometric functional analysis. Suppose I now have two norm linear spaces, X and Y, real norm linear space as usual. And B of X, Y will be the vector space of continuous linear transformations from X to Y. Sometimes called bounded linear transformations, as they're bounded on the unit ball. The elements of this are bounded on the unit ball of X. And we use the usual operator norm on B of XY, defined by the usual formula that you see in a first course in functional analysis. If Y is a Banach space, then B of XY is a Banach space with this operator norm. Doesn't matter that X is or isn't. Now, this result is really attractive. I can't say who did this first. Maybe I did. Maybe Pino and Aze did. But anyway, it's very straightforward, and it's a good exercise. Suppose I have these two norm linear spaces, and I have a sequence in B of XY. So let's equip X cross Y with the this max norm. It's the box norm. But you could equally well add the two guys, norm of X1 plus norm of XY2. But the box norm is probably more usual. Then Tn converges to T in the operator norm if and only if the associated sequence of graphs for the linear transformations. Now, those are subspaces of X cross Y, closed subspaces of X cross Y. I get operator norm convergence if and only if I get Atouche-Wetz convergence to the graphs with respect to the metric determined by the box norm. And there are all sorts of other results like this. So our last application, again, involves convex sets. So let A be a non-empty set. It doesn't have to be convex. And we'll talk about the polar of A. The polar of A lives in the dual space. It consists of the elements of the dual space such that for every A in A, X star of A is less than or equal to 1. But what that is a sublevel set of the support function. It's a sublevel set of height 1 of the support function. So again, this is called the polar of A. This will be a closed convex subset of X star. Actually, weak star closed, but I'll just say this. So the polar of A agrees with the polar of its convex whole. We have this identity called the bipolar theorem. That's what it's called in functional analysis. X and X, such that X star of X is less than or equal to 1, for every X star in the polar is the closed convex hull of A union the origin. So this is a basic resultant functional analysis. So we all usually denote this set by A polar polar, but that's an abusive notation because A polar lives in X star. So its polar rightfully lives in X double star, but still that's not. And by this formula, if A is closed and convex, and 0, the origin is contained in A, we have the closed convex hull of A union, the origin is the closed convex hull of A, which is a closure of A, which is A. And so the mapping's an involution, so restricted. So here's one theorem that you might like. Suppose I have a sequence A1, A2, A3 of closed convex sets in X, and A is a potential limit. If AN is a two sweats convergent to A, as determined by the norm, then this associated sequence of polars converges to the polar of A with respect to the operator norm of the space. Okay, so now we'll come back to epigraphs for a little bit. So I said it, this definition 5.6, but I didn't write it down until now. If I have a function, which is an extended real valued function on X, doesn't take on value minus infinity. Its epigraph consists of the points X alpha in X cross R, so alpha is greater than or equal to X. It's stuff on or above the graph, the real graph. If XD is a metric space and you have a function which is extended real value, then F is lower semi-continuous in any way you learned it in your classes, if and only if the epigraph is a closed set product. Another reason why you want to look at epigraphs, if you have a norm linear space and F is a convex function in the usual sense, there's a standard inequality that expresses convexity of function, then this is equivalent to the epigraph being a convex subset of the product. And the last result, I think, is pretty attractive. Suppose I have a sequence of non-empty closed convex sets in my norm linear space. The following statements are equivalent. AN is a two sweats convergence to A with respect to the metric generated by the norm. 2, the epigraph of the distance functionals for AN is a two sweats convergent to the epigraph of the distance function to A. So these epigraphs live in X cross R. The third condition is the epigraph of the support functionals for the members of the sequence is a two sweats convergence to the epigraph of the support functional for the limit. These sets live in X cross R. So notice that 1 and 3, this complements Hormander's theorem. Hormander's theorem tried to express convergence of closed and bounded convex sets in the Hausdorff metric to convergence of the support functionals. But the sets had to be bounded. 1 and 3 don't require the set. The equivalents of 1 and 3 don't require the sets to be bounded. Well, I've spoken for an hour and a half, and that was my charge. So that's it.
Okay, so thank you, Professor Bia. So it was really a nice talk. Before, with your request, I would like to ask participants for questions if they have.
Yeah.
Yes, if anybody would like to ask any question, yeah, you may please raise your hand.
I want to ask a question.
Okay, Yogesh,
Am I audible?
yes, Yogesh, you are audible. So he is Professor Bia. He is my third student actually. He would like
Okay.
to ask a question.
So, sir, very good evening to Professor Gerald Beer. It is an honor moment for me to interact with you. Sir, I'm reading your book, Topology on Closed and Closed Convex Sets from
Yeah.
several months. Sir, you have told about a representation of vitreous topology as a weak topology. So, is there any such representation present for Feld topology also?
The what?
You have mentioned a representation of vitreous topology as a weak topology with varying compatible matrix and X over X. So is there any such representation present for Feld topology also?
Feld topology. God, I should know that off the top of my head. It's probably the case using excess and gap functionals. I just don't remember off the top of my head. My God, I wrote the book 30 years ago. But what I would look for is weak topologies involving, say, excess and gap functionals, where the fixed arguments aren't or the fixed arguments are compact sets. But there's a paper that I wrote with Sandro Levin and Camillo Costantini on it's called something like gap and excess functionals and Born-logical convergence. And this topic is considered more generally there.
Okay, sir.
And if you don't have it, write me and I'll send it to you. But the Feld topology is, can I say something about the Feld topology since you brought it up?
Yes, sir.
Yeah, the Feld topology is interesting because this idea of a two-Schwetz convergence, if I replace bounded sets by compact sets, then I get convergence in the Feld topology.
Okay, sir. Okay. Sir,
Okay.
second
Yes,
question
yes.
also.
So these are both examples of so-called Born-logical convergences.
Okay. Sir, like for defining Weisman topology or Taussberg's topology and Hausdorff metric topology, we need our base space to be a metric space.
I don't know about Weisman topology, but certainly for the Atush-Wetz topology and the Hausdorff metric topology, you can work in uniform spaces. In fact, Michael worked with the Hausdorff. His Hausdorff metric topology was defined in uniform spaces, so he didn't work in metric spaces.
Okay, sir. Okay, thank you.
I don't know how many people have worked with the Atush-Wetz topology for uniform spaces, but you'd have a uniformity associated with this enlargement condition.
Okay.
And you could work with that to do various things. So one thing that I don't think anyone's done, I don't understand why. I put up this theorem about, I have operator norm convergence of linear transformations if and only if I have Touche-Wetz convergence of the graphs.
Yes, sir.
What happens if we work in on continuous linear operators, nets of continuous linear operators between locally convex spaces, for example, and I define the Touche-Wetz topology in the product in the natural way? Do I have that theorem going through? I don't think anyone's ever looked at that. I'm too old and tired to. So
Okay.
maybe you can. You understand what I'm saying?
Okay, sir. Thank you. I should try.
Yeah.
Yeah, thank you, Yogesh. So we have one more participant who would like to ask a question. Yes, Dr. Mishra, you may please ask a question.
Thank you for giving me a chance to ask the question. Thank you, sir. And good morning to all of you. Sir, I would like to one question.
It's night time here.
My question is a very simple, that what is the recent development on the study of invariant for the function space under the hyperspace topology, and how you see the scope of such type of the study?
This is not my area. That's all I'm going to say.
Okay.
Like cardinal invariance and things like that, right?
Yeah.
It's not something I know anything about. I don't do set theoretic topology.
Okay.
I'm a fake topologist. I'm an analyst. I'm sorry. I don't do that kind of stuff.
Okay. Thank you, sir.
Yes, anybody would like to ask any more questions? Yeah. Okay. So I think so there are no more questions from the participants. So with that, we thanks Professor Beer for introducing a very interesting topic to the participants. And of course, it is beneficial for us also. And also he has presented few more applications to motivate the participants towards this area, which is of course a very active area of research. And I hope Professor Beer will be available if there is any question in future also. So if we can ask
I
him.
hope one day to visit Jaipur again.
Yes, definitely
beautiful
we would we would be happy to host you any time.
Okay.
Yeah, thank you very much, sir. Thank you.
Good night or good morning, as the case may be.
Yes, sir. Good night, sir. Good night. Yes.
Bye.
Bye. So our next session will start at 2:30. That will be a session on fixed point theorems in Banach spaces. Again, a very interesting area of research. So I request all the participants to be there on time. So at 2:30. So thank you.